In this video, I'm going to be comparing three function families: linear, exponential, and quadratic. All right, so a linear function as an equation, there are three different ways that we can write a linear function. We can either write a linear function as in slope-intercept. And in slope-intercept, our linear function is going to look something like this, where we have y equals negative 2/3 x plus 5. We can also write a linear function in standard form. And standard form, we would look something like this: 2x plus 3y equals 15. We can also write a linear function in what's called point-slope form. And point-slope form would look something like this, where we have y minus 3 equals negative 2/3 x minus 3. So the idea of this video is that by looking at an equation or a graph or a table, we'll be able to recognize whether we're dealing with a linear, exponential, or quadratic function. Right, so the way that I know that I'm looking at a linear function, if I look at these particular equations, is that I have no visible exponents. My variable x it does have an exponent. It's the exponent of 1. But there's no visible exponent here, or there's no exponent of 1 for any of my variables. So this has to be linear. Let's look at how an exponential equation looks. Well, let me just write down a couple of examples. We have y equals 2 to the power of x plus 3, or y equals 6 times 3 to the power of x minus 4, and y equals 4 to the power of x minus 3 plus 1. Now in this case, I know I'm looking at an exponential function because my exponent is the variable. Here the exponent is the variable, here the exponent is the variable. I can see that here my exponent is the variable minus 3, but nevertheless my exponent is the variable. It's going to change at each step if I want to know what's happening at the first step or the second step. The exponent is the thing that changes. Now a quadratic like linear can be written in three different ways. We can write a quadratic in standard form. Standard form looks something like this: y equals 2 times x squared plus 4x minus 2. Or vertex form, that looks like something like y equals 3 times x minus 1 squared plus 4. And factored form, that looks like y equals x minus 4 times x plus 3. Now if I look at the quadratic equation, I can see that the exponent in this case is squared. In fact, that's what quadratic means. Quadratic means squared. If you consider Spanish, cuadrado is squared. So we have 2x squared. Because of the square, it makes it quadratic. Here in vertex form, we have the square as well. Our exponent is squared. Now factored is a little tricky because I don't see any exponents as well. You might be confused and think this is linear. But if you were to distribute and multiply this binomial times this binomial, you would end up having standard form, which would then show that I have a highest order exponent of 2. So graphically, here's my Cartesian grid like this. If I have a line, well, that's what linear means. So if I ever have a line graphically, the line is going to indicate then that we're dealing with a linear function. As an exponential, here's my Cartesian grid. If I'm converging at one level, at one, y equals some value, we'll say in this case y equals 0, and then on one end we converge, and the other end we just shoot off to infinity, then we know we're dealing with something that is exponential. We could end up having something that's also exponential, like this. Oh, we just did that one. How about like this? This is an exponential decay. It's also possible to have an exponential that looks like this or like this. So the point is, for any exponential graph, we're looking at converging on some value at one end, either end, and then blasting off or shooting off either to negative infinity or positive infinity on the other end. Quadratic functions always make a parabola. You're going to have this U-shaped graph. Now, it's possible to have the parabola open downward, but as long as you have a U-shape, if your graph makes a U-shape, then you're dealing with a quadratic. Let's look at a table for linear. For linear, we have x on one side, a y on the other. This is also called a t-chart. And then the x value, we need to verify that the x value is in numerical order. If this x value is not in numerical order, we might examine the y value and think that it's linear, but in fact it's not. We'd have to examine it a little bit closer. So let's say that we have this sequence of 5, 8, 11, 14, and 17. And if we look at the first difference, in this case, I see that my first difference is going to be plus 3. So, in fact, that is a telltale sign that you're dealing with a linear function. So, if our first difference, in this case is a constant, which means that we are adding or subtracting the same number at each step, then we know that it's going to be, we're dealing with a linear function. Well, how does exponential, when we look at an exponential table, how does that compare? So here we have an x, y. Again, we need to make sure that our x values are in numerical order, and then we can examine our y values. Well, let's do 6, 12, 24, 48, and 96. Now, if we look at this sequence, we can see that we are multiplying the same amount at each step. So in the case of, if we multiply or divide at each step, then we know we're dealing with an exponential table. Let's look at quadratic. Now, quadratic, I think, seems to be the most confusing for students. So again, my x value is going to be in numerical order. And then we'll have some quadratic like 9, 19, 33, 51, 73, and 99. And if we look at our first difference, well, 19 minus 9 is going to give us 10, and 33 minus 19 is going to give us 14, and 51 minus 33 is going to give us 18, and 73 minus 51 is going to give us 22, and 99 minus 73 is going to give us 26. This is our first difference. Our second difference, if we look at 14 minus 10, that's going to give us 4, 18 minus 14 is going to give us 4, 22 minus 18 gives us 4, and 26 minus 22 is going to give us 4. This is our second difference. So if our first difference is linear and our second difference is constant, then we know we're dealing with a quadratic. So if the first difference is linear and the second difference is constant, then we know the table is quadratic. And I'm going to do one bonus problem. I had my students do the diagonals. I had my students do the diagonals of different polygons. And the diagonals, as the vertices increase, the diagonals, they become quadratic. So if I have 3 vertices, this is my x value, this is my y value. So we have our t-chart. If I have 3 vertices, I have 0 diagonals. If I have 4 vertices, I have 2 diagonals. If I have 5 vertices, I have 5 diagonals. 6 vertices, 9 diagonals. 7 vertices, 14 diagonals. 8 vertices, I have 20 diagonals. Now let's look at our first and second difference. Our first difference is going to be, well, 2 minus 0, that's going to give me 2, and 5 minus 2 is going to give me 3, and 9 minus 5 is going to give me 4, and 14 minus 9 is going to give me 5, and 20 minus 14 is going to give me 6. My second difference is going to be, well, 3 minus 2 is 1, 4 minus 3 is 1, 5 minus 4 is 1, and 6 minus 5 is 1. So we know then this is proof that we're dealing with a quadratic function. So anyway, I hope this was helpful, and I hope you have a wonderful day.